we will be continuing in this room with the second of our two Moon talks, and this one is called One Small Signal for a Man, deploying LTE communication on the Moon. And let's bring some more Nokians to the stage now. Paweł Cebula graduated from the University of Technology right here in Wrocław, and he has been handling machine parts, measurement, signal processing for machine vibration diagnosis, heating appliances, and 5G at Nokia. As a recent father, he feels a strong obligation to find somewhere his kids will be safe, and his latest destination idea is the Silver Globe. Paweł. Now, during the day, Błażej Michalik is a technical leader at Nokia, where he's working on creating APIs for automating all the things related to BTS. Notably, he's involved in sending Nokia's LTE network to the Moon, and at night he works on open source projects which include developing small OS kernels. Well, don't we all? His hobbies are music, finding novel ways of crashing systems in production, and placing emojis in those places where people do not expect to find them. Błażej. And the third speaker, Rafał Słoma, is a developer and Python trainer here at Nokia. As a space and quantum physics enthusiast, he automates processes by introducing new tools and simplifying those existing ones. When not thinking about conquering the Moon, he plays board games and sometimes frequent squash courts. Rafał. So, one small signal for a man deploying LTE communication on the Moon. Enjoy.
Okay, hey there, or as we are on a conference organized by Nokia, telecommunication company, I shall probably start with ahoy, as once Graham Bell suggested, that this greeting should be beginning of each telephone call. So let me rephrase the start. Ahoy there! Okay, so warm welcome on the second presentation of our project, this time called One Small Signal for a Man, deploying LTE communication on the Moon. This lecture is divided into three parts. The first part, and my part, will be about mission challenges. Then Błażej is going to share software aspects, and final part, conducted by Rafał, will be about hardware. Okay, let's start. Challenges that we have faced and ultimately mastered. So I divided them into three groups. The first group, journey effects. It covers two effects, vibration and shock. Then landing area. There I will describe challenges from the Moon South Pole perspective. And the last one, space effects, moon effects. There we will touch effects such as multipaction, lunar dust, and a couple more. Okay, so let's start with journey effects. So the rocket launch is generally a controlled and sustained explosion which generates two big threats to integrity of any transported equipment: vibration and shock. So the vibration is especially caused by the rocket engines and the enormous friction created when punching through the Earth atmosphere. Vibration is interesting because it doesn't necessarily disappear as it gets further away from its source. So the small levels of vibration at the bottom of the rocket could lead to amplified vibrational loads on our payload, which is at the top of the rocket. So worth to mention here is the fact that all unanticipated vibration could be, or even will be, potentially catastrophic for us. The second phenomenon here is shock. So our system needs to survive, of course, shock from the initial launch, but I would say that's relatively minor consideration compared to the shock generated by the separation of the rocket parts. But once the final rocket parts separate and we escape Moon atmosphere, the hard part is over. In no other leg of the journey will we encounter these severe stresses that we experience during the 10 minutes of the flight. 10 minutes will be so critical for our mission. And touching down the lunar surface will, of course, produce some shock and vibration, but they will be nothing compared to the shock and vibration generated at launch. Okay, as I mentioned, Shackleton, no, I didn't mention it, sorry. But let's move to the landing area. We will be landing on the lunar South Pole, and the exact place will be reached near the Shackleton crater. So the lunar South Pole presents some interesting physical challenges that we need to overcome. And these are sun angle, terrain properties, and temperatures. I will start with temperatures, as it is the main factor that impact our equipment redesigns. So while we won't be dealing with the bitter cold of lunar night, we still need to deal with temperature differentials between the sunlight and shade. Moon has no atmosphere, so there is nothing to trap ambient heat. So therefore, there is a big difference in temperature between objects directly in the sunlight and objects in shade. So for instance, our LTE antennas will be exposed to, I would say, warm and cozy temperatures of around 20 degrees of Celsius on the side facing sun, and few centimeters away on the opposite shaded side of the antennas will be enduring freezing temperature below minus 100 degrees of Celsius. Next challenge from that group is terrain properties. So kind of obvious thing that LTE signal propagation depends on the terrain properties. Therefore, height of the antenna is the critical factor in determining whether we can maintain a stable connection between the base station and our vehicles. To account for this factor, we have done extensive tests and simulation using digital terrain maps and developed propagation model to evaluate radio quality signal on our landing area. And last challenge from that group, sun angle. So on lunar South Pole, sun is always just above the horizon, which will have a big impact on the operation of our mission. Lighting condition depends on the time of the year. Therefore, we are timing our mission to maximize exposure to the sun. Our landing area will be fully sunlit for the entire duration of our mission. And last group here, space moon effects. Here we will touch following effects: ionizing radiation, multipaction, solar minimum and maximum, and lunar dust. So let's start with ionizing radiation, which is the most concerning for the sensitive electronic. Why? Well, it removes electrons from atoms, leaving atom in a net charge, and that means atom become an ion. So when ion concentration changes, then the electric current flowing through the transistor will change as well. We have two main sources of ionizing radiation. So the first one, galactic cosmic rays, the most damaging. I will explain it why in the next slide. And the solar flares and coronal mass ejection from sun. So why the galactic cosmic rays are the most damaging? So let's imagine a single ionizing particle passes through the semiconductor material, leaving enough energy in active area of the circuit that it has undesirable effect on the circuit. So it could lead to unexpected path for electric current to flow, or less damaging for hardware issue, but still crucial for software issues like bit flips or logic errors. The next effect in that group, multipaction. Multipaction occurs only in space in radio frequency devices. It is rapid multiplication of electrons, which lead to discharge, it generates radio frequency noise. It drains output power and increases temperature of the device. Solar minimum and maximum. Well, why I put it here? Because here, not here, but also here, in this year, we have a solar maximum, and operating in solar minimum is the worst case scenario due to the fact that there is a less solar wind deflecting galactic cosmic rays ions. And last here, but not least, lunar dust. Lunar dust is, I would call it tough opponent for our mission because due to its characteristic. It is high adhesive, it is high insulating, and due to the constant bombardment of electrons and protons from the solar wind, it is negatively charged, and moreover, it is floating a few centimeters above the lunar surface. All these characteristics will impact thermal surfaces, which can be degraded by the lunar dust, or conductive elements which can be damaged by the discharge of accumulated electric charge. Okay, so all these challenges that we are working to solve to ensure successful mission are complex ones, but on the other hand, they are fascinating problems. But for sure, lessons learned from this mission will be important and invaluable for us and for future development of wireless communication in space. But with regards to complex and fascinating problems, let's see what software part is going to surprise us with. Warm welcome to Błażej. Powodzenia, będzie dobrze.
Check. Yeah. Thank you, Paweł. Let's see if I can operate the slide. Right. So I'm going to start this with a little bit of a story. Imagine that you are working as a software engineer for a telecommunications company, and one day, as you're going through the office, your manager pulls you to the side and says, "We've got a new assignment for you." So we've got a client. We are going to give the client this box. We are going to connect some LTE hardware to this box. We need the box to take in some commands, automate the LTE network, and give us some data about it back. And we want to put your software inside of it just to make it work. So what do you say? And at this point, you might start planning something like, all right, we have like off-the-shelf LTE software automation stuff. We can put up a REST framework somewhere over here, put up a Grafana dashboard there to visualize the data. Well, looks easy, right? So you say, we might need 1 or 2 months to figure out all the details, but in general, it's like, I'm gonna have a prototype for you in by the end of the week. And your manager is happy, and as you slowly step away from the whole situation just to go for your daily dosage of caffeine in the kitchen, your manager snaps his fingers and said, "All right, I forgot. They are going to send this to the moon." So no problem, right? Well, you thought that this is going to be easy. Well, software is software, right? It's just going to run on the moon. So, in the immortal words of Jeremy Clarkson, how hard can it be? So, in the next few minutes, I'm going to show you how changes in the environment influence the way we develop software for this mission. And I'm going to show you 3 examples. The first one being latency. So when you develop a project like this, one of the first things you're going to notice is that A, the moon is pretty far away. B, the speed of light is awfully slow for your use case. So the moon follows a 27-day elliptical orbit around the Earth. And if you measure the 2 closest points between the 2 bodies, you're going to have between 356,000 kilometers and 397,000 kilometers. And taking the speed of light into account, this leaves you with like around 2.5 seconds of round-trip time. This is the shortest possible physical time for communications between Earth and the moon. This does not include like satellite relays, those satellites coming in and out of view from the perspective of the antennas on the Earth, and so on and so forth. This is the shortest possible physical time. So, is that a lot? Let's put it into perspective. So this is the Jeff Dean's latency numbers every programmer should know. So like on the left here are the super fast things your CPU does. And as you go to the right, there's like local APIs, then there's local network, all the way to sending data between the continents. And the cool thing about this graph is that as you go from the left to right, there are points where the techniques you use change, the protocols change, the architectures change. Overall, the interfaces feel different. So now let us put our numbers on this graph. It's absolutely enormous. And so this already influences the way we design the interfaces for our mission, because the operator in the missions room, in the event of the emergency, we don't want him to wait several seconds for output of one command just so he can issue another. right? So we need to be careful about the scenarios we are designing our interfaces for. And then the protocols, the communications protocols are going to change. Right off the bat, I can tell you that you would not be able to use vanilla TCP in space. On these time scales, it just doesn't work. Right, and this goes a little bit more into the topic of interplanetary internet, where unfortunately we don't have time to talk about this. But if you'd like to learn more, here are some pointers that you can Google. The delay-tolerant networking is the major term which you can research. There are easily findable research papers on this topic. Right. Next challenge. So as we remove our software from the atmosphere of the Earth, as we move our software out of the atmosphere of the Earth and out of the magnetic field of the Earth, we are going to get bombarded with the radiation, just as Paweł said minutes ago. And for our CPU inside our box and the software that runs on this CPU, this means that there's going to be a lot of random behavior and crashes. So we need to do something about it. The first thing that comes to mind is obviously shielding. Shielding works, but it's boring, it's also heavy. We will not be able to get enough shielding for our mission. We need to find other ways. Now, the next thing that comes to mind, well, we have one processor here. Why not have three? Let's put some logic on top of those three processors that checks those processors' outputs. And if one of them is out of whack, let's just scrap it, reset it to the last known state. And voila, we have triple modular redundancy. This is something that SpaceX uses for the Falcon 9 rocket avionics. This is cool, but obviously it increases the cost. There's going to be more power draw just because you have to compute everything 3 times. And in many of these schemes, just because you have to synchronize 3 different points of computation, you get, unfortunately, you'll get degraded performance. So let's maybe look for other ways. And most of the ways we are going to improve radiation resilience comes from the fabrication method of the actual transistors. Ever since Intel developed the first processor using the photolithography, we've been getting performance increases thanks to the fact that we make this process better, that we shrink the feature size, that we can project smaller and smaller features on top of the silicon. Now, in the year 2020, 2 things launched. First, there was the M1 silicon, M1 MacBooks by Apple. That uses 5 nanometer process. The second one was the Curiosity rover. And so the Curiosity rover was launching on a top of a rocket, going to Mars. But this is using in the vicinity of a 200 nanometer process. And the cool thing about the Perseverance rover is that Perseverance uses the CPU that was originally based on the CPU that was used in the G3 iMac. So you have an Apple product there and something that is based on something that uses similar CPU. Right. So why does the rover use the older fabrication method? Well, it's because, all right, if you go towards the lower feature sizes, you might get better performance, but it is unfortunately the case that if you use the older fabrication methods where the transistors are bigger, then for many different reasons, your radiation resilience is going to be better. Right. So what that unfortunately means for us, software developers, is that a lot of the schemes by which we improve our radiation resilience are coming down to the fact that we will have less performance and less CPU cycles to play with. So for a mission like ours, the unfortunate thing is that, like, where web developers have something called mobile first, just to make the web pages look better on mobile, what we have is performance first. Whenever we are introducing a new component to our software, we have to actively think how that will impact performance when we are going to scale it, or when the software is going to have like constrained resources. We need to be mindful of the performance constantly. Right. I've told you about two things related to the physical environment, but there's also something that I call the economic environment of software. And the economic environment has its own mechanics. So one of the basic mechanics of these economics is that whenever you increase the cost of failure, there's less room for error. And so maybe when you are developing one of your projects in your daily job, it might have looked something like this. You have some planning, a bit of design goes into it, then there's developing, and then a little bit of testing and QA. Maybe it looked something like that. Maybe there was more planning or designing, whatever. But if it looked like this, and you strap it onto a multi-million-dollar rocket and point it on the moon, then it's suddenly gonna look like this. And there's gonna be a lot more testing, a lot more design talks, a lot more quality assurance. And all right, testing is good, so more testing, more better, right? So what? Unfortunately, this also means that there's gonna be slightly more resistance to change. Like if you have this wonderful idea for this great refactor, you are going to spend a lot more time convincing other people and proving that it works after your change. So basically, there's gonna be more, if it ain't broke, don't fix it. Right. So, summarizing, I've shown you 3 different ways in which the environment influences the software design part. And the cool thing about this is that whatever challenges we master over there, the lessons learned from those challenges are going to be immediately applicable for the software that we design and develop here on Earth. But our software is worthless without the hardware to run it on. And for this part, please welcome Rafał Słoma.
Thank you, Błażej, for introducing me. And now, let's take our network to the moon. During my part of the speech, I would like to present you few interesting things. First of all, I would like to introduce our 3 vehicles, so lander, rover, and hopper. Next, I would like to describe a little bit how LTE networks looks like on Earth. What changes has to be to take it to the moon, and how it will look like on the moon. So do not waste any moment, and let's introduce first vehicle, Intuitive Machines Lander, aka Nova C. Lander is a major part of our mission and will carry all other payloads to the moon. It has automatic landing and hazard detection technology. We put it LTE BTS, this base transceiver station, on it, as also 2 BTS's antennas. And there is also deployable rover garage. Next, just mention it, into Lunar Outpost MAP, aka rover. MAP is mobile autonomous prospect platform and will drive around landing site and allow us to measure network performance in different ranges. To do so, it will carry Nokia UE, so user equipment, so kind of mobile phone, and 2 LTE antennas, and will communicate over LTE with Nova C lander. Last but not least part of our mission is Intuitive Machines Micronova, aka Hopper. Micronova is propulsive drone that we deploy off Nova C lander and hop across lunar surface up to 25 kilometers from the initial landing location. It will carry Nokia LTE user equipment and 1 antenna and communicate with a Nova C lander over LTE network. And now let's bring our stuff to the table. So we are not only sending BTS to the moon, but we are deploying entire LTE network there. On Earth, LTE network allows us to call, text each other, or access the internet services. However, as it is, it cannot be taken and used on the moon. I will give you some examples of a modification a little bit later, but now I would like to describe how it looks like here on Earth. So we have a radio sites. You can know them from buildings or towers. And we have LTE users. So all kinds of smartphones, MiFi, cellular routers, even new cars have a LTE. But from the network perspective, all of them are users, UEs, user equipment. They communicate through the radio site and backhaul with next core component, literally, which is Evolve Packet Core or Core Network. It's a piece of software that do, among many other things, signaling, session management, and acts as an external gateway for the internet. Then is a transport medium like fiber or cable, and it allows us to access to the internet. So I would like to introduce very important rule whenever it goes to the space hardware, which is swap rule. What it means? Don't answer. I give you the answer. You can read it as a size, weight, and power rule. In practice, it means that anything that goes to the space should have smallest possible size, smallest possible weight, and smallest possible power consumption. Why is that? An idea? Okay, I give you the answer again. Because there is nothing in space. We have to take everything from the Earth. So whenever any component has a bigger size or bigger weight or bigger power consumption, is the wasting of resources. And of course, wasting of money. Because every gram of payload has its price, really big price, when it goes to the moon. Next thing which I would like to do is shortly compare Earth and Moon condition. Paweł already mentioned some of them, But let's correct them all together. So on the Moon is smaller gravity and smaller radius than on Earth. There is no atmosphere there, which is so common on Earth. There is no humidity, also available on Earth. No wind, present on Earth, but there is a radiation. On Earth is a small radiation rate. Here we have mild temperatures. On the Moon there are extreme temperature swing, even between -100 and +100 within a few inches. We have forests, animal, buildings on Earth. On the Moon there is electrically charged lunar dust. Crater on Earth in opposition to craters. And of course, on the Earth we have people. There is no single man on the Moon within 386,000 kilometers. So our network have to be self-deploy, self-configure, automatically operate, and self-heal, as we can't send anyone to plug the computer to the debug port. As you can see, Moon conditions are the hardest we know of. If we can build LTE there, we can use those learnings to improve our products and services on other extreme environment here on Earth, like deep mines, oil rigs, or nuclear power plants. So, what we've done to make sure that this will work? Of course, we test a lot. First of all, we didn't allow any animal to enter with room with BTS. There is no animal on the Moon. Next, we've used NASA and military standards. For example, we put our components on the shaker table to simulate shocks during the launch and during the landing. We've used giant centrifuges to simulate acceleration forces during takeoff. And of course, we put it into vacuum chamber to simulate environment on the Moon. We've also completed a real-life drive testing in Colorado. Through the network, we've connected engineering development units, EDUs, of the configured in the same way and similar, basically same as those for the lunar mission. We were able to establish connection between Lunar Outpost Map Rover and Intuitive Machines Hopper with the simulated version of Nova Sea Lander. Through our network, Lunar Outpost Mission Controller was able to send commands to their vehicle and transfer images back from it. Intuitive Machines perform similar mission simulation. However, Hopper movement were entirely simulated, as its rocket engine can't achieve a necessary thrust in Earth gravity. Moon gravity is smaller. We, as a Nokia, executed mission procedure and tested our network in different ranges. We were thrilled that during the test, network extend mission targets every inch. We've done countless simulation lab tests, but there is nothing in comparison to take everything in real site and test in real life. From each test, we measured the network, measured the responses, identified the weakness, addressed them, and tested again until we were fully satisfied of the network performance. If results, we changed some component to the lighter version of the developed fully new one. First, we created new thermal mechanical housing for our network. On the Earth, many systems rely on convection to displace heat. It's normal and natural for all of us. But space is different. Convection doesn't work on space because there is no air. So we have to use a different approach. On our solution, we've used conduction and radiation to displace the heat. This method works also on Earth, however, is slower. So we don't use it as a main cooling way. However, it does not require any medium. It requires only a surface. So it works without air on the Moon. Next is to integrate Evolve Packet Core into LTE BTS. On Earth network, Evolve Packet Core usually works on separate computing units. However, on our case, less is more. I hope you remember swap rule. So we've integrated Evolve Packet Core into same BTS into same case. And now, let's check how it will look like on the Moon. We have a lovely render on our landing site. There's intuitive machines lander and lunar outpost rover. Let's add network graph, how it will look like. So we have radio site and Evolve Packet Core integrated into single case and mounted on Nova Sea lander. There are also two LTE BTS antennas mounted on lander. Next is a UE, so device to allow communicate with the network. You can think about it as a mobile phone, which is mounted inside Lunar Outpost rover. There are also two rover antennas mounted on it. And we have mission control on Earth and direct connection to it through the deep space network. As we are running to the end of my speech, I would like you to remember that we are building first LTE network on the Moon. Nobody did it before. It's not the simple stuff to build LTE on the Moon. It requires a lot of tests and changes and tests and over and over and over and over. On behalf of myself and on my colleagues, so Błażej and Paweł, thank you very much for your attention.
Let's do it properly. Rafał, Błażej, Paweł. So much stuff and 3 speakers, so let's have some questions, if you will. Anybody interested? Any questions, insights? Yes, let's start over there, please. Thank you.
As long as we can answer them, so.
Yeah.
I would like to ask, will the software contain any correction methods for issues such as bit flips and possible other computational or logic errors that may be due to radiation?
I can confirm that we know of techniques to do that, but we unfortunately cannot tell you anything about how the software will work and handle that in the actual missions. Maybe this will be revealed in the papers that will follow afterwards.
Any more insights? Yeah, one over there.
Hi.
Hi.
So, since there are a lot of solar winds, solar storms, and moonquakes, what will be the estimated average lifetime of the instruments?
Oh. Well, the estimated lifetime isn't the thing we are actually worried about, because from what I know, I think I can share this. Yeah. This is going to, the lifetime is going to exceed the actual mission parameters. So I would look at the mission parameters that are going to be announced by the Intuitive Machines company, and we expect our hardware and instruments to exceed that.
Hi, it's a bit of a pessimistic question, but nevertheless, it seems that quite a challenging spot was chosen for the landing. So even in terms of the moon, I believe 2 out of 3 last missions that attempted for the lunar south pole have failed. So all these plans are really cool and ambitious, but are there any plan B in place in case of if the landing does not go well?
Well, I think that actually one of the missions landed. I'm not sure, but
Not yet.
not yet.
Not
All
yet,
right.
yeah.
So that is really a question for intuitive machines, not for us. But in general, we need to trust the knowledge and the expertise of the guys there. They were working very hard to ensure that the landing side there are no issues with the landing, and you know, I think that it was the Japanese mission that failed because of changing the landing site at the last minute, which was very unfortunate. But so yeah.
There is no plan B at the moment, yeah, for sure.
Yeah, if we crash, then there's obviously no plan B. If there's going to be a rapid unscheduled deconstruction on the moon, then...
Was at any point quantum computing considered? As we know, it's far more sensitive to radiation. Is it completely off the table to pursue it in terms of space exploration?
Sorry, can you repeat?
Quantum computing, was it at any point considered? As we know, it's far more sensitive to the radiation. Is it completely off the table to pursue?
I'm not sure, Błażej, if we can reveal this because it's,
I'm not
technical details,
sure if I can reveal the focus areas of our colleagues at Bell Labs, but in general, there are specific things that the program from NASA calls for, right? And in general, the tipping point program from NASA was about putting the actually tested here on Earth technologies into space. I'm not sure if quantum computing is in that category right now, so...
I think it was the Schrödinger's quantum computing. It was there, but it wasn't there, and the choice is yours.
Yeah, right.
Błażej, Rafał, Paweł, thank you.